Hi, I'm Gabriele Manganaro. This is a high-level overview of the course entitled Multi-Gigasample per Second Nyquist DACs from Theory to Silicon. This will take place this coming September, and it consists of 8 2 hours-long lectures. There is no rigid prerequisite to attend this course, although mastering analog IC design is certainly important. We will begin the course with a quick refresher on core concepts to establish a shared theoretical foundation and terminology. From there, we will cover relevant signal processing fundamentals, as they are also important for some DAC applications. We will also discuss various modeling techniques that we will eventually apply, particularly during our calibration lectures and for simulation during hands-on practice sessions. DACs are relatively complex systems requiring the use of multiple abstraction levels, ranging from system and architecture abstractions and all the way down to physical design and even at device level. While architecture and system level concepts are very important, we will always refer back to transistor level and physical implementations. Besides the fact that different concepts are best captured with different representations, alternating between abstraction levels will be important to develop intuition and to find solutions to different problems. Additionally, some of the techniques that we will cover are not just important to meet performance targets. They are also important for the systems embedding the DACs and driven by final application requirements. Our primary focus will be on current steering DACs, since these are most common in high-speed, high dynamic range applications. But we will also take a look at examples of alternate architectures, such as charge distribution and inverter-based DACs, which offer different advantages, disadvantages, and trade-offs. For example, current steering DACs are often the best choice to linearly and efficiently drive a low impedance load with a wideband output. Unfortunately, voltage headroom is a serious challenge. On the other hand, many of the inverter-based and charge-sharing emerging architectures get around the voltage headroom problem, but these either require a wideband impedance matching network to be placed before the actual output load, or they require highly linear continuous time buffers, which can be even harder to implement at the DAC itself. You can immediately spot integrated inductors that are bigger than the DAC themselves in some of the die photographs. In the end, it's all about matching the right solution to the problem and about trade-offs. The topic of non-idealities is one of the most important ones. Very small imperfections can have visible impact on the DAC spectral performance. Understanding the source of non-ideality is the first step toward their compensation. For instance, any array of transistors will be subject to manufacturing gradients or to power line IR voltage drops. This, in turn, will lead to corresponding parametric shifts. If we design our DAC so that the input code control for these devices lead to gradients to build up errors on the output, then strong harmonic distortion will develop. On the other hand, if we simply change the order of activation of subsequent devices while the individual mismatch errors don't change, the correlation between the mismatch errors and the output is broken. As a result, the spurious output power spreads over the output noise floor instead of building up on harmonics. There are many non-idealities to discuss, and we will cover the most common ones originating from manufacturing and device imperfections, to those originating from the circuit design and the physical implementation of individual subcircuits, to the networks that connect them and their mutual interactions. And we will see how each of these effects impact the noise and linearity performance of DACs, leading to harmonics, tones, spectral artifacts, colored noise, etc. Understanding where these errors come from, how they manifest themselves, and having suitable models for them is a solid starting point to develop techniques or circuits that can mitigate them. That leads us to the other important topic of mitigation, calibration, and cancellation circuits and techniques. We will discuss different mitigation techniques for these imperfections, including dynamic element matching and how this can be used to turn spurious power concentrated at specific frequencies into broadband power that is uncorrelated with the signal we are converting, as well as various forms of calibration and correction methods, including those that measure and compensate the imperfections where these originate, as well as others that estimate the impact of the imperfections to the output, but instead of acting on the imperfection itself, actually remove the spurious power from the output spectrum. And we will evaluate their effectiveness and associated trade-offs, complexity and cost, and in terms of power consumption, area, design time, etc., etc. And again, we will put the suitability of different approaches into the application context. For instance, some of the calibrations are best run when the DAC is powered up and before it is used to perform its conversion job. But parametric shift happening during normal operation won't be corrected. On the other hand, if we run the calibration while the DAC is in normal conversion operation, we need to ensure that it does not interfere with the output synthesis and that the errors we want to correct are properly estimated. Additionally, a system using the DAC may be running independent calibrations at the same time, such as in the case of a power amplifier digital predistortion. So it's important to ensure that the concurrent correction loops do not interfere with one another. High-performance DACs are constructed from large arrays of unit circuit cells that must meticulously routed over significant silicon areas and operated synchronously with picoseconds level precision. Consequently, routing and placing each constituent block to minimize interconnect parasitics and mitigate spatial mismatch. It's a complex combinatorial optimization puzzle with many trade-offs and dangerous traps. Implementing robust floor planning and layout techniques is therefore critical to minimizing these physical impairments. So we will spend some time understanding strategies and associated compromises and compare these ideas with published examples of remarkable DACs from both academia and industry. We will also dedicate time to interleave DACs, now becoming commonplace for gigahertz operation. While these architectures enable the direct synthesis of RF outputs with exceptional dynamic performance, they introduce unique technical challenges that require specialized calibration and compensation techniques to ensure output spectral purity. Interleaving spectral artifacts are essentially spurious images of the converted signal, originating from mismatches among the interleaved DACs. Therefore, some of the techniques required to mitigate them find inspiration from traditional DAC mismatch mitigation methods, while other approaches are quite specific to the different nature of these problems. We will discuss high dynamic range DACs, suitable for wireless applications or instrumentation, as well as lower resolution but very high output rate DACs, which find applications in wire communication systems, satellite communication, and so on. And again, after discussing each case, we will always evaluate the effectiveness of each approach to assess where it is useful or how it could be improved if it needs to be improved. While most of the interactive lectures are classic presentations, this course includes 2 practice sessions where we will take a look at targeted simulations, discuss practical design techniques, and even common errors and ways to troubleshoot problems. This alone is a subject that is both not well documented and yet crucially important, because inherently modern data converters are large and complex with hundreds of thousands of devices that need to be accurately simulated over millions of cycles to be able to get, for example, an appropriate output FFT. Brute force simulation is a non-starter. You need to be very careful in deciding what you're about to simulate, what are the right conditions, and how it can help you finish your design successfully and on time. That will be a crucial part of what we will be covering during these practice sessions. To keep our practice sessions grounded and engaging, we will focus on two complementary examples using GlobalFoundries 22 nanometer FTX technology. A 14-bit 1 gigasample per second DAC that is typical for wireless applications, and a 7-bit 28 gigasample per second interleaved DAC geared toward wired communications. While complex design like this typically requires several months of interdisciplinary and detailed engineering work, we will focus on the core circuits and the relevant design and simulation techniques to give you a practical, hands-on feel and an experience that complements our more theoretical lectures.